In this video, we're going to solve this example of a mechanics problem using Lagrangian mechanics. So what we're dealing with here is a pendulum that's hung from the ceiling of this railroad car. Now, to make things interesting, this car is actually accelerating to the right here with a constant acceleration. And that imposes what is known as a forced constraint. That is a constraint that depends explicitly on time. I should say that in order to, I want to specify a coordinate system here. So this will be the x direction to the right and then y direction downward. So let's now follow our recipe again here. Ensure that non-constraint forces have a potential. Well, the only potential available is the gravitational potential. There's nothing else going on here, so that works out fine. Now the generalized coordinates, well, we have one object that's moving in 2 dimensions, x and y. So we have 2 unconstrained coordinates. We have one constraint. That's a stiff pendulum. So that should give us one generalized coordinate. And I'm going to use phi for that. Next, we should write down the potential and kinetic energies, and again, inertial coordinates. Now, the railroad car is accelerating. Because of that, phi is not in an inertial reference frame, so I would not try to attempt to write down the kinetic energy using phi. So I'm going to just use x and y and then make the change of variables. So starting with the kinetic energy, I don't have to think. I just write down 1/2 m x dot squared plus y dot squared. Same thing for the potential energy. We already have it there actually. That's minus mgy. Simple enough. Now for the constraint. So I'm going to actually call this position here xc. That's the position of the x position of the car, specifically the point where the car is, where the pendulum is attached to the ceiling in here, inside the car. So the first thing we need to do is write down, well, we have to write down this constraint here, which basically says that the position of the pendulum, x and y, has a specific relationship to the top here, the ceiling of the car. And I'm going to do this in 2 equations, even though there's only one constraint, and then at the same time change variables to phi. So that's why we have 2 constraints. We have 1 constraint and 1 variable change, so that means we have 2 equations. So what does that say? Well, x minus xc has to be equal to L sine phi, and y minus 0, because I'm taking 0 to be the top of the rail, the top of the ceiling here. That's going to be now L cosine phi. In other words, x equals xc, but xc equals 1/2 at squared. Because the car is accelerating towards the right. There might be some initial velocity and position too, but we'll take those to be 0. So we get then that x equals 1/2 at squared plus L sine phi, and that y equals L cosine phi. Put a little box here to show what I'm actually after here. Now, because we have explicit time dependence here, that means that the Lagrangian is going to depend explicitly on time as well. This type of constraint is known as a forced constraint. And that changes things a little bit. Okay, if we have this, we can now also write down the time derivatives of this. So x dot is at plus L phi dot cosine phi, and y dot is just L phi dot times minus sine phi, put the minus sign in front. All right. So that's it as far as the physics is concerned, at least for a while. Now I'm going to write down the kinetic and the potential energy by substituting these into the equations. That's a little bit of algebra, but the physics is done. So I'm going to go through this fairly quickly, and presumably you know how to do this. If you can get to this point, the rest is just turning the crank. Let's add to 1. At this point, it's always a good idea to check that the units work out. Everything inside this bracket should have the unit of velocity squared. So we have here acceleration times time, that's velocity squared, that's velocity squared. Acceleration to time is velocity. This is meters per second, that's velocity, so that's velocity squared. Same thing over there. So that unit seems to be working out. Then we have the potential as well. All right, so let's see where we are now in terms of our things here. We've written down the constraints, we've changed the variables and applied the constraints. Really, these two should be just 1 point. Because if you apply the constraints and need to change the variables, you probably do it at the same time. Then we write down the Lagrange equations and solve it as best we can. So that's the next step here. So we have the Lagrangian. So let's then calculate the generalized force, because we only have one variable left, that's phi, so this will only be one of those. And remember, now we take derivative with respect to phi. We don't have to care about phi dot, it's a constant as far as this derivative is concerned. Forgot the m there. Then we have a generalized momentum. apply the Lagrange equation. The generalized force equals the time derivative of the generalized momentum You can see that this term here is actually the same as that term there. So they go away. So that's the equation of motion. Now, it's a little bit hard to recognize this, so I'm just going to remind you here that what we're doing is we're adding something times the sine function of phi plus something else times the cosine function of phi. And we can actually do this and write the whole thing as just the sine function of phi plus an angle. We've done this before when we dealt with oscillators. We'll do it again here. Right, because g over g tilde is cosine of delta, a over g tilde is sine of delta. And then we can recognize this where, so what we really get here now is this. So that's a solution. Now this looks just like the equation of motion for a regular pendulum, okay, with a couple of differences. One difference is, of course, that the amplitude here, or the frequency that we're going to get for small deviations from the equilibrium, omega, has this form, right? So the square root of j squared plus a squared, and that inner square divided by L. The other thing is that the equilibrium point is located at some angle minus delta. Other than that, it looks just like the normal differential equation for a regular pendulum. So what we get in here is that this pendulum will swing around some new equilibrium point here that's located at minus delta, so it's in the opposite direction of the acceleration here. So it will swing around this point, and the frequency of oscillation is going to be given by this expression. So the acceleration that normally would be just g in here is now the Pythagorean sum of g and a, the acceleration of the car and the acceleration due to gravity. But other than that, the pendulum inside the railroad car behaves just like a regular pendulum.